Hello, it's Ms. Sunil Kargi. Today I am going to share you about virtual lab experiment, where I have done the experiment on the topic of logic gates, and I study the different logic gates by using the virtual labs. To do this experiment, we are using the Vlab websites. Okay, there is an website where we can do the experiment, and generally we can do experiments by two types in two ways. Okay. uh, in a real lab experiment and virtual lab experiment. Okay, so I'm going to share you about the virtual lab experiment. How did I do all of this experiment, and how can I do these experiments? So I'm going to share you. Okay, so to share this experiment, first of all, I have to go to the share of screen. This is the share of screen, and this one my terminal. To save this one. Okay, all right. Now here it is. Okay, this was my first slide. Okay, and I'll keep this my photo in here, and I'll make it a little bigger. Again, beginning, full screen. Okay, okay. This was my first slide. Okay, the topic of my experiment is study of the logic gates NOT and OR NOR and NAND using TTL method in virtual lab. Okay, and which is submitted by me, Sunil Karki, and I am a MSc first semester student, and I'm a 2079 batch, and this was my roll number, and this was my contact number, and this was my mail ID. And this experiment, I have to submit it to our HOD, Central Department of Physics, Kashmir, Nepal. Give us me a task to complete this virtual lab experiment. So I have to submit this experiment to our HOD, Central Department of Physics. Okay, to go to the next slide here. Okay. Mhm. Okay. Okay. Um, study of the logic is, this is my title of the experiment. Study of logic is or and. Okay. Sorry. Study of logic gates or and nor not by using TTL method in a virtual lab. And abstract, this was my title. And abstract, first of all, is abstract. Okay, in the study of logic gates includes understanding the properties and behavior of different types of gates. Okay, uh, generally in a logic gates we study the understanding the properties and behavior of different gates. Okay, how the NAND gates behave, how the AND gate behaves, how the OR gate behaves, how the NOT gate behaves. Okay, and there are various performance. So we study about the various difference, which are analyzing we analyze the truth tables and logical equation associated with the with each gates, and how the output of the gears will be vary on varying the input terminal, while what will happen when we make the input terminal high and low, whether output will be high or low. And where we here we study the here I study the different gears. Okay, that's logic gears in a logic gates operation in a virtual lab. Okay, and we show that the on the prediction of the input, the output of the logic gates also varied based on the logic operations. Okay, which I have found in this experiment by using virtual lab. And the next one is the keywords. Okay, keywords is just it's a virtual lab, and I often use this or in this experiment and logic gears, obviously in the topic of our experiment. That's why maybe it will be automatically with use of one line and electronic circuit, and another is logic operations. Okay, so this one are the these are the keywords. Okay, keywords uh, this experiment which I have chosen for in here. And I have to go to the next slide here. Apparatus, okay. Generally, apparatus, I was to conduct the experiment. It's not a real life experiment. So I have done in a laptop, okay. So one of the apparatus is laptop here, and sometimes I'm using the mobile also. So it is not necessary if you have a laptop here. So I'm using mobile also. That's why I write down my experiment, and this is a website, okay. And which this is a website. It is a system, okay. It is a system which I have used. That's why I have included an apparatus, okay, and MS PowerPoint, okay, and Zoom, okay, virtual video website where I have done all the experiments, okay, all the experiments. And if you do the real lab experiment, you need the breadboard, transistors, jumper wires, okay, and power supply, okay, and resistors. These are the apparatus which you require if you do a real lab experiment, okay. But in virtual lab, all of these materials, all of uh, these components are really available in virtual lab experiment, and we just have to be connect them by virtually, okay. If you have to go to the website, and you have to do the experiment. What are and you have to do the experiment there. You have to vary the input, and you have to get the output. You have to go the respect individuals. There are the different gates that is available in the website, and you have to check the logic operations, and you have to try to understand the you have to try to verify the truth tables of these different gates, okay, by using virtual lab experiments. And so these are my apparatus that I used is in my experiment, laptop, mobile, MS PowerPoint, Zoom, virtual lab. So I have to go to the next slide here. Okay, now introductions, okay. Introductions of my topic, okay. Introductions of my experiment, okay. And generally electronic circuits that implements the basic and common logic operation are called the logic gates circuits, okay. First of all, we have to know about what is logic gate circuits. Logic gate circuits means electronic circuits that implement basics and common logic operations, okay, are called the logic gate circuits. And the gate implementing an operation is AND gate, okay. If the gate is implementing the AND operations, then it is called AND gates. And that implementing OR gate means it is OR operations, it means OR gate. And if that is implementing NOT operations, then it is called the NOT gate, okay. And the logic 1 represents the high level, and the logic 0 represents the low level, okay. And the circuit is a bipolar semiconductor, is the basic element or integrated on the silicon chip with a certain logic function. It's called a bipolar logic or integrated circuit or TTL logic gate circuit, okay. And it is a kind of logic gate circuit, okay, commonly used in a digital electronics, okay, which has been applied earlier and is relatively mature, okay. And and ATTL is mainly composed of the BJT, okay, and bipolar junction transistor and the resistor. It has a fast speed. The earliest TTL gate was the 4074 series, and the 74 series, 74L series, and other series appear. However, because UTL has a larger power consumption, it is gradually replaced by the CMS circuits, okay. And this was just simple introductions of the experiment of logic-based experiment. Okay, now to go to another slides. Okay. Okay, next is literature review. Okay. Literature review is what are the research experiments which are done in a previous time, and what are the things is remaining to identify. To know that, we have to do the general literature review. So logic gates are fundamental building blocks of digital. From digital review, I have found those things which I mentioned here, and I'll share you here. Okay, I'll describe you what are the things I found from the literature review. Logic gates are the fundamental building blocks of the digital electronic circuits that are the responsible for performing logical operations on the input signal and producing the corresponding output signals. Okay. And TTL, transistor logic, is a popular method for implementing logic gates using bipolar transistors. Okay. So TTL is a popular method for implementing logic gears using the bipolar transistors. Okay, we are using the bipolar transistors, and we only find out the logic operations. Okay, in the literature review, there are several studies and publications that have focused on the design, analysis, and applications of the logic gears using TTL method. Here are some key findings from the literature review. Okay. Rule number one is TTL logic gates design. Okay, there are numerous studies in the literature that have presented different design techniques for implementing TTL logic. Yes, for example, in the study of AMD Landis and MW, they presented a comprehensive design methodology for TTL logic gates that includes the use of standard TTL chips and custom design circuits to improve the performance and reduce power consumption. Okay, and to design, how can we design the TTL logic gates designs? Okay, what is the how we can design the TTL logic gates? Again, TTL logic gates analysis. Okay, the performance analysis of TTL logic gates is a crucial aspect of the design and optimizations. Okay, and very several studies in the literature have focused on analyzing the delay and power distribution, noise margin, and other performance parameters of the TTL logic gates. Okay, so, and the application of TTL logic gates. Okay, what are the application of TTL logic gates? The TTL logic gates find numerous applications in digital electronic circuits, and such as microprocessor, memory devices, and communication systems. Several studies in the literature have focused on the application of TTL logic gates in these areas. Okay, so these are the literature review which I found here. Okay, and comparison with the other logic families. Okay, so TTL logic gates are not the only the method for implementing logic gates. Okay, there are several other logic families. Okay, CMS, ECL, yes, that are used for this purpose. Okay, okay, and the several studies in the literature have compared the performance and the characteristics of the TTL logic gates with those of other logic families. Okay, so okay. In a conclusion, the literature review reveals that there is a significant body of research on the design, analysis, and application of logic gates using TTL method. Okay, and this method offers several advantages. Okay, such as simplicity, low cost, and compatibility with other TTL devices, making it popular choices for implementing digital electronic circuits. So these are the this is the conclusions on the literature review. Okay, now theory. Okay, theory of this is the theory part of my experiment. Okay, and logic gates are the elementary building blocks of any digital systems. Okay, and for input, and it have one or more than one input, and only one output. Okay, and for the high one voltage output we call 1s. Okay, and for the low one we have to call uh, 0s. Okay, and there is a relationship between the input and output based. Okay, and based on the logical operations. Okay, and based on these logical operations, the gates are the different types. Okay, and some are OR gate, some are NAND gate, some are AND gate, and some are OR gate. Okay, some are NOT gate, and some are NOR gates. Okay, based, it depends on what is the operation on that gate and what will be the output, and what will be the output on varying the input terminal, and the relationship between the input and output terminal, the gates are different based on the logical operations. Okay, and there are the two in here. There are two gates which are considered as an universal gates. One is the NAND gate and or NOR gates. Okay, these gates are considered as an universal gates because from these two gates we can derive the fundamental gates like OR gate, AND gate, NOR gates. Okay, so these are the universal gates. Okay, NAND gate and NOR gate. So first of all, I'm going to discuss about the AND gate. Okay, on the theory part, I tell you something about the AND gate. Okay, so this one is a logical operation. This one is a logical symbol. Generally we represent it logically by this symbol on the AND gate. Okay, and this is the truth table. Okay, truth table here, and in truth table we found there A, B, and this is the input terminal and this is the output terminal. When we make both low, it will be low. When one terminal is low, one terminal is high, output will be low. When one terminal is low, high, now one terminal is low, and then output will be the low. When both terminal high, then output will be the high. It is based on the logical operations. I later on I'll show you. So because the above expression was based on this expression, okay, this on this logic operation, okay, y equals to the a dot b. The AND gate is sometimes called the all or nothing gate also, because nothing gate, because the AND gate is sometimes called the all or nothing gate. When all the inputs are high, then output is high. That's why it is all gate. Otherwise, output will be low. That's why it is called nothing gate. Okay. And another gate. Okay. Another gate is OR gate here. Okay. And this one is an OR gate. Okay. The OR gate is sometimes called the any or all gate. Okay. Any or all gate. Okay. When all inputs are low, then output is a low. Okay. And otherwise output is high. Okay. In a OR gate, when all the inputs are low, okay, then output will be low. Okay. So, and when any one of the input is low, then output will be the high. Okay. So to get output low, both terminal have to be low. Okay. Otherwise we get the high gate. Okay. In other case we get the high gate, high output on the OR gate. Okay. And this is the logical symbol. Okay, logical symbol for the OR gate. We generally use this symbol for the OR gate. And this is the truth table. Okay, this is the input terminal, this is the output terminals, and A and B, output is C, and we vary the input 0 0 and 0, output is C, and 0, output will be low, 0 1 1. Okay, and this one based on the logical operations y equal to a plus b, also in next slide. Okay, this is a Boolean expression for the OR gate. Okay, on the basis of this operations, the output terminal will be vary. Okay, if there is a 0 1, it will be y equals to 1. That's why it is high. So that for the if the any one of the input will be low, then output will be high. If both input are low, then output will be low. That is the OR gate. Okay, now I will go to discuss the next gate. Okay, next gate is NOT gate. Okay, the NOT gate is often called an inverter. Okay, because it just gives the opposite output. Okay, if input is low, output will be high. If input is high, and output will be low. The NOT gate has only one input and one output. Okay, it has only one output and only one input, one output and only one input. Okay, so the job of the NOT gate is to give an output that is not the same as the input. Okay, so if you want to get a different output with respect to the input, then you have to use the NOT gate. Okay, so this is the logical symbol and truth table. This is the logical symbol for the NOT gate. Again, this is the truth table for the NOT gate. Okay, 0 1. If input is 0, output will be high 1. When input will be 1, output will be 0. Okay, so I'll go to the next slide to show you the what is the Boolean logical operations. Okay, a Boolean expression for the NOT gate. Okay, this is the Boolean expression for the NOT gate. Y equals to a complement. Okay, if A is low, output will be high. If A is high, output will be low. This is the based on this Boolean operation expression, the logic NOT gate will be works. Okay, all right. Now another gate is NAND gate. Okay, NAND gate is called the universal gate because all other the fundamental gates are derived from these gates. Okay, that's why we call the NAND gate is an universal gate. And in this gate, both input is high, then the output will be low. If in other case, all we will get the high output voltage. Okay, just only in when both terminals have the input terminals have high voltages or high when all the inputs terminals are when both the input terminals are in high state, then we will get the low output. Okay, on the other cases we found the high output. Okay, and this is the logical symbol for the NAND gate, and this is the truth table for the NAND gate, and this is A and B. This is the input terminal, and this is the output we will get at NAND gate. Okay, A and B output, and this will be the truth table for the NAND gate. Okay, and the Boolean expression for the NAND gate is y. This is the Boolean expression here. Boolean expression I have just paste it here. Okay, C equals to the or y equals to the A dot B of whole complement. Okay, this is the Boolean expression. In terms of C, we can write down y also. If you compare with the previous slide, okay, y equals to the A dot B whole complement. Okay. Okay. Now we have to go to the next slide to talk the next gate. Okay, that is the NOR gate. Okay. NOT gate. In NOT gate, both input is low, then the output is high. Okay. In when the both input is low, okay, then the output will be high. In other cases, all the output will be low. Okay. So in the NOR gate, this is a logical symbol. This is a logical symbol for the NOR gate. Okay. This is the NOT gate here. Look at here. This is NOT gate, and this is OR gate. Okay. R plus not. Okay. R plus not is a NOT gate. Okay. And this is the input. Terminal if is input. Okay, and this is the output Q or Y. Okay, 0 0 1 1 0 1 0 1 0 0 1 1 0. Okay, so to get output high, the input terminals, both input terminals should have to be the lowest state. Okay, now next slide is Boolean expression. And this is the Boolean expression for the NOR gate. Okay, Y C equals to the A plus B of whole complement. Okay, A plus B of whole complement. Okay, Y equals to the, that will be the NOR gate. Okay, all right. So first, and in this terminal, I am just in this slide, I am going to discuss about the experimental circuits of the NOT or experimental circuit of the actually NOT gate. Okay, this is the experimental circuit for the NOT gate, and by using the TTL method, we are using one transistor. Okay, this is the lead, this is the power supply, and this is the resistor here, and this is the resistor here. In this is the collector regions, this is the emitter regions, this is the base region. Okay, and from the base we give the input here. See the one terminal here, and we have to use the NOT gate, and we are trying to find trying to verify the truth table of the NOT gate by using the transistor here, and this is, and by using this transistor we will make the NOT gate here. Okay, now we'll verify the logical operations of the NOT gate. So in the base terminal, we are applied the resistor is taken the 1 kilo ohm, or you can use a 10 kilo ohm also here. And this is the 1 kilo ohm resistor here. And this is from here, we take the output, this is the lead here. Okay. And this is the experimental setup. This is the experimental circuit. Okay, not setup, experimental circuit of the NOT gate by using transistor. This is a transistor. Okay, we are using only one transistor to make the NOT gate operations. Okay, to get the NOT gates, we have to use only one transistor. All right. Okay, this is for the NOR gate. Okay, we are using three transistors. No, two. Yeah, two transistors here. Okay, two transistors we are using here. 1 and 2. Okay, and this is the base part. Okay, here. This is the base part here. Here, this is the base part, and 1 kilo ohm, 1 kilo ohm, and T1 and T2, and I'm calling it 1 kilo ohm. This is the lead here. This is the power supply. Okay, and this will be the 100 kilo ohm resistor here. So from this this is an experimental circuit. Okay, it's an experimental circuit for the NOR gate. Okay, okay, and this is for the OR gate. Okay, and OR gate we are using the three transistor 1, 2, and 3, and this is the VCC. We have to supply from the input here. This is the input. Okay, this is lead here, and this is the VCC supply from here also connected here. Okay, and this is output from and lead, and by based on this on the circuit we can get the OR gate. Okay, and so using three transistor here, and if you follow the circuit here, and we can get the OR gate. Okay, we can get the OR gate. Okay, and NAND gate. Okay, this is the four transistor here. Repeat here, 1, 2, 3, 4. In this circuit, we are using 4 transistor here. Okay, and A and B, R1, R2, R3, R3, R4, T1, T2, T3, and T4. And this is the diode, LED diode, light emitting diode, 5 volt. Okay, and this is there, and 0 volt. Okay, and this is the experimental setup, and this is the experimental circuit for the NAND gate. Okay, and another is AND gate. Okay, and this is again I've already discussed AND gate. VCC. Yeah, this these transistors I have already done this experiment. It's a circuit. Okay, and this is the AND gate. Okay, now okay, now we are going to discuss about them. I'm going to discuss about the methodology. Okay, methodology Here is a methodology for implementing logic gates using the TL transistor logic in a Vlab. Okay. How can we do this? First of all, I will show you the points here. Okay. Just open the Vlab. Okay. We have to open the Vlab and create a new project. Okay. And add the detail chips you needed to for your projects. To do this is click on the add component and button and just search for the detail chips you need. Okay. Okay, you can search for this 400 chips which is quad 2 input NAND gate, okay, or 274 chips which is quad 2 input AND gate, okay. So this is the methodology, and next point is to connect the power supply to the circuit. Okay, we have to connect the power supply circuit, and then while we apply when after we while we apply the power supply the circuit, then the circuit will come on the operations here. And the next point is to connect the inputs and output to the logic gates. Okay, to just click on the connect button and then the click on the pins you want to connect. You can you can you can connect these inputs one chip to the outputs or another devices chips. You can connect them switches or output devices, okay, or other input devices, okay. And if you are then you have to go to the next and the next point is test your circuit by simulating it, and click on the run simulation button to see if your logic gates are functioning as expected. You can use the digital probe tool and your outputs of your gates, okay. Okay, and check the values of the inputs and output values, okay. And modify your circuit is needed. If you want to modify your circuit, you can have to if you needed to modify your circuit, you have to modify. If your circuit is not working as expected, you need to make certain changes on connections or components, okay. And after you completion all the tasks, you have to you once your circuit is working correctly, you have to save it, okay. Or completing whole task, you have to save it and export it, use for other projects or simulations, okay. And TTL logic are sensitive to noise and can be damaged by static electricity. Make sure you handle them carefully and anti-static precautions while working with them. So I'm going to share you news here, okay. I'm just how can I do the experiment? Let me have to go here. Yeah, I'll go to here how I'm doing the experiment in VLAB. Okay, I have to go here and look at here. This is I'm already opened this terminal. You have to go on the offside and type the virtual lab for the logic gears, and this terminal will come. You will find out these gears. So I will go to the AND gate. Okay, how did I check it? The AND gate. Okay, how did I do experiment on the AND gate in a virtual lab? Okay, I go to the AND gate. I'll just show any one. Otherwise, the video will become very long. So I'll do only 2-3 and get only the. All right. This is instructions you get from here. You will get the instruction. How can I use this experiment? How else to do? What do you have to do? What are the procedures to do experiments? Okay. And this you can get from here. Look at the instructions. You connect the battery, press the switch 1 for the battery to be connected to the circuit, press the switch 2 for the input A and switch 3 for the input B. The switch is on the state is that it will be light, it will glow, it is green state, okay, and switch is off state, it is a red light, okay, red light state. The LED does not glow if both if any one or both of the switches 2 or 3 are off and glows only if the both is switches 2 and 3 are on. This is symbol the LED in the off state. This is the LED in the off state, and the LED in the on state is it will be glow, okay, or it will be glow, okay. All right, and then experiment to perform AND gate on a kit, okay. This is the circuit which is performed on a kit, okay. And AND gate using the resistor transistor logic RTL. These are the two transistor here. I'm using two transistor here, okay, in an AND gate, okay. Transistor T1, transistor T2, transistor 1, transistor 2, switch to A, switch 3B, okay, and PNP transistor. You can use PNP transistor also, but circuit will be different one, okay. We have to exchange this polarity, okay. And register 3R3 and register R4 and LED, and this is the LED here. And first of all, you have to check, okay. You have to click here and it will be connected, and you have to click switch 1, it will be on. And then if you make A high and B low, output will be what? 0. So there will be no glow on the lead. But if you make both high, look at here, the output will be high. So the lead will be glow up. Okay. If you make input A is low, one B is high, then it will be not glow. It will be low. That's why it is not glow. Okay. If you break both input low, then it will also not glow because output will be low. So from there, it is from this lead, from the glow of the lead, we know that the output of the AND gate is high when both input are high. Okay. In other cases, output will be low. So, and another is simulator, and next simulator we will verify the value. Okay, whether the logic operations. So the formula here is given y equals to a dot b, and you will give the one. Will give one here for a, and both its input is high, and then what will be happen if it will be high? Yes, in our we assuming it will be high. So whether it will check right or not, it is correct. Okay, and if a will be low, if a will be low and b will be high, output will be what? It will be low in the AND gate. Okay, that's why it is check. Yeah, here. Okay, it is correct. Okay, if you make both, if you make both low, and output will be high or low. Low, yes. What I will do here, high. It will be wrong or right? It will be wrong. Let me see. It will see right or wrong. Okay, incorrect. Yes. If you make both input low and output will be high, it is incorrect. So it verify this promise to stable. We verify that AND gate is high only when both input are high. Okay. Similarly, we can we can do the another gate. Okay, I'm going to do NAND gate. Okay. Okay. This is the same NAND gate. NAND gate kit. Okay, this is the keys here. This is the two transistor given here, switches A and B. Okay, you have to connect here. Switch on A. Okay, and switch A. It will be glow. Okay, in NAND gate, if only one in NAND gate, if both are high, then it will be not glow. Okay, on other cases it will be glow. If you make one input is low, it will be glow. If you make both input is low, it will be glow. If you make this one is low, this one is high, it will be glow. Okay, this is the condition. This is the conditions we satisfy these are the all the conditions. Okay, all of the conditions it's satisfied by using this circuit. Okay, by using the circuit we verify the NAND gate. Okay, and from the truth table also will, and the simulator we just check the truth table here. Okay, our expected results for the NAND gate is if both the input are low, if both input are high, okay, then it will be low. Okay, if we make low, okay, check it here. Okay, correct. Yeah, but if you make a one here, it will see incorrect. Look at, because this is because a logic operation is a plus b, a dot b of whole complement of a dot b. Yes, so if we say incorrect, look at it, incorrect. Yeah, so but in other cases it will be high. If you make a 0 0 and it is high, is correct. Okay, in this way you can do you can check other values. Okay, like you exchange 1 0 1 1 0 0 1. In this way also you can check it. Okay, so this one is drawn for the NAND gate. Okay, and in this way we can do in the NOR gate also. Yes, and this is battery, and 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 this one is for two stable for here. Okay, NOR gate. Okay, and for OR gate also similar OR gate also here. We similar to take the source table. This is for to you can read whether it will go or not. Okay, and to confirm this to get logical operations. Okay, Boolean expressions. We have to logical operations to verify. Okay, from there. And in this way, not get also same progress, not big deals. Okay, and similar to 2, and this is a not get. Okay, so this is the site where I've done this experiment, and I verify the all these truth table and logical operations. Okay, And this is the theory, and this procedure simulation process. So you have to go to the simulations, which is the all the experiment. Okay. All right. Now I have to go to the next part. Okay. Okay. Which I'm discussing on the methodology. Okay. Now observations. Okay. What did I found from this experiment? Okay. So I'm going to show you the observations. Okay, this is the observations which I found from this experiment. I already share you the calculations. How did I do calculations uh, on the outside on the simulations terminal, simulations, simulator 1, simulator 2, and from that experiment, and from that experiment, so if I found this two, this one. Okay, this output. Okay, this result. Okay, actually. Uh, these are, and from observation, so I found all these things. Okay, while I make the one input high, okay, and while I make the input over a high, input will be high, I will get output one high, and this is correct. I just check only correct. Okay, zero. If we make one a high, zero, one v high, I get output output low. That is also correct. When I will make the what I will make the output input terminal input terminal A high, input terminal B zero, I will get output zero. That is also correct. When I make the input terminal A zero, input terminal B zero, output terminal B zero, that is also correct. This is for the AND gate. Okay, I've checked on the AND gate, NOR gate, and not NAND gate, NOT gate. Okay, I've checked all the logic gates. Okay, this is the truth table. So I have verified for the NAND gate from the website. Okay, so which is already provided in the virtual lab. Already the experimental setup. The connections between transistor, um, leads, okay, registers, power supply, they are already connected there. Okay, but if you do in the real life, you have to do your by yourself. You have to connect yourself. Okay, and then you have to check the logical operations. Okay, and you will check the output voltage, input voltage. Okay, and this way. And the next slide for the next gates. Okay, and this is for the OR gate. Okay, in this way, in A terminal I make low, B terminal high, output will be high, but if I make both input low, output will be high. Is it possible for OR gate? No, this will be incorrect. So it is incorrect. Okay, so you can see which one is high, which one is in which case it will be high, which case it will be low, and we can see from there also. So and it verify the truth tables for the OR gate. Okay, for the NOT gate. Okay, for the NOT gate, this is the it have only one input and one output, and this is correct. For if you make the input low, output will be high, and if you make input terminal is low high, output will be low. So I just check only two part only. But if you make input terminal low and output terminal is low, it will see incorrect here. Okay, so in this way also you can check this whether the results will be correct or incorrect from the virtual lab experiment, which I've already shown you in the in the previous slide. Okay, all right, now NAND gate. For NAND gate also, I've checked the NAND gate also here. I found the when the one is interrupt terminal is low and one is high, I get a one output. I check that it is correct. And when both input are low, it is output will be high, and it is correct. It is possible. It is the output will be low when the both input terminal are high. Okay, that is the correct. If you make one, this one is zero and this one is one, if you check this right on zero, it's not correct. It is incorrect. In this way, you can check the output whether it was correct or not. Okay, and next slide. Not and not get for a not get for the NOR gate. I'm just using this one. Terminal is 0, B terminal is 1, output is 0. Is it correct? And this way you can check for the other logical operations. So other inputs also, and exchange inputs terminals high and low. But if you make 0 and 1 and this will be 1, it will be incorrect. Okay. If you have 0, 1 and you write on one output, it will be safe. Because in a or a NOR gate, it is not possible that when you make one input terminal low and one other terminal high and output terminal high, it is not possible. So it's not found in the OR gates, okay, in real lab also. So it's incorrect in a virtual lab. Okay. So if you make one input low and output high, output will be low. So it is correct. It will be correct in the virtual lab. All right. So what are the advantages of the virtual lab? Okay, in a virtual lab experiment, what is the advantage? Okay, what are the advantages of the virtual lab experiments? The virtual number one is so make some I've written down some points. What are the advantages of the virtual lab experiment? And the number one advantage of the virtual lab experiment is there are several advantages. Okay, over traditional physical experiments, including it is cost effective. Okay, so if you want to do experiment in a real lab, okay, it will be a little bit costly. Okay, you have to buy the instrument, and it is a little bit expensive. Some instrument are a little bit cost expensive. So due to the cost effective, due to the high cost, you cannot maybe some experimental cannot be proceeded, and so they are not able to do an experiment. So to do an experiment, what will be the to make an idea what will be the output? Okay, we can use these virtual lab experiments. So it is a cost effective. Okay, so virtual experiments are generally less expensive than the physical experiment, as they do not require costly equipment and materials or facilities. Okay, so we can make a simulations in a in a ways in our website, or we have to use the simulations there, and we can do the experiments in the virtual lab. Okay, and it's a flexibility. Okay, and virtual experiments can conduct at any time. Okay, we can conduct any time. Okay, and anywhere and without being limited or the physical constraints. There are no constraints, time, locations, weather conditions. There was no any restrictions. Okay, we are literally free as compared to the real lab experiments, to do the lab experiments uh, uh, in a lab, in a virtual lab, actually, not in a lab. Okay, real lab, not in a virtual lab. And reproducibility. Okay, reproducibility in virtual lab experiments can be easily reproduced. Okay, and repeated. Okay, we can do repeatedly the same experiments and allow research to validate and verify the results. Okay, more efficiently. Okay, so we can do experiments in repeatedly. Okay, and it is a little bit safety also. Virtual experiments eliminate the potential risks associated with the physical experiments, such as exposure, hazards, materials, injury, and damage of the equipment. Okay, so it will be uh, more safety as compared to the other experiment. Okay, and data collections. Okay, in data collections also, then virtual experiments can generate large amounts of data quickly and accurately, so making it easier to analyze and draw the conclusion from the results. Okay, what are the results which I found, and we can draw the conclusions from the data collections. Okay, from these results which are found from this experiment. Okay, and accessibility. Virtual experiments are accessible to a wider range of people, including those with the disabilities who may not be able to participate in a physical experiment. Okay, those people who are not able to go to the lab, do the experiments, they can do the experiments virtually, at their home, and they know the what will be the desired results. Okay, what will be the output, what is the procedures to follow the experiments. Okay, they can learn the experiment from the virtual lab. So that is these are the advantages of the virtual lab experiments. Okay, and another is ethical considerations. Okay, virtual experiments can avoid ethical concerns associated with the physical experiments that involves animals or human subjects. Okay, it is ethical considerations also. And overall, the virtual experiments can offer the research a cost-effective, flexible, safe, and efficient way to conduct the experiment and collect the data. Okay, these are the benefits of the virtual lab experiment. Okay. Even though there are many advantages in the virtual lab experiments, there are some limitations also. Okay, so I'm going to discuss some limitation on this slide. We virtual lab and VLab also have some limitations. Okay, which are the limited realism. Okay, virtual labs may not be fully replicated the complexity and nuisance of the nuisances of the physical experiments, making it difficult to simulate real world scenarios accurately. Okay, it will be difficult to simulate. Okay, in real world scenarios accurately. and the limited interaction. So we cannot do interact, we have to do self, okay? And virtual labs may not be provide the same level of hands-on experiments on physical labs, limiting the ability of students or researchers to develop practical skills and knowledge, okay? We cannot do interactions here, and it will be, so that's why it limits the our practical skills and knowledge, okay? Okay, and the technical requirement. Virtual labs requires computer, software, and the stable internet connections, which may not be readily available or accessible to everyone. Okay, if there was some students who have no access of internet or computers, and they cannot do the virtual lab experiments. Okay, so it is difficult for those students who are not able to purchase the computers or have no internet. They cannot do the experiments. So this is also one of the drawbacks of this virtual lab experiments. Okay. And another is limited experimentation. Okay, some experiments may not be suitable for the virtual labs. So such as those that require the use of dangerous or real materials, or those that involve large scale equipment. Okay, so which those experiments which requires large scale equipments, and so if the so it is not possible to do in a virtual lab. Okay? So this is limited experimentations. Okay, so it is a limited experimentation. And the limited customizations. Okay? Virtual labs may not allow users to customize experience, limiting the ability to tailor experiments to the specific research or educational needs. Okay? And lack of collaborations also. Okay? Virtual labs may not facilitate to collaborations and teamwork, especially as physical labs, which can be essential in the certain fields of the research or execution. If you are going to do some research experiment, research works, and there is it's a huge topic, okay, and then so at the time you need the collaborations, okay? So in the some if there's some research works which needed collaborations on that topic also, we cannot do the virtual lab experiments, okay, efficiently. So these are the drawbacks. And now I'm going to next talking on the next slides. Okay, what are the precautions which I have to follow? Okay, or what are the precautions? Okay, for the virtual labs while you are doing the virtual lab. What are the precautions you have to follow while you are doing the virtual lab experiments? Okay, when using the virtual labs, it is important to take some precautions. Okay, what are the precautions to consider? Ensure safety and accuracy of results. Some precautions to be considered included. Follow the instructions carefully. You have to follow the instructions carefully. Okay, so VLabs often come with the instructions, and it's important to read and follow them carefully to avoid the errors or accidents. Okay. So you have to be very careful on whether they have some error or not while you are doing the experiments. You have to be very careful on that things, and you have to follow strictly the instructions given in the simulations. What are the steps you have to follow to do experiments in the VLabs? And use appropriate equipment. What are the equipment needed to conduct the experiment? You have to use the appropriate equipments to pursue these research works. Okay, ensure that you are using the appropriate equipments. Okay. And observe the safety implications. VLabs may involve potentially hazardous materials or equipment, and it's important to observe all the necessary precautions, such as wearing protective gear, working in a very internal area, avoiding exposure to the chemicals. Okay, and verify the results also. Okay, virtual experience may not always provide accurate results, and it is important to verify the results through the independent testing or comparing them to the published data. So you have to verify. Okay, I've already mentioned to that there are some errors, so you have to follow the instructions strictly. So and you have to verify again. You have to verify your results. So whether to the already available data. Okay, so and then you can be sure that my experiments give the expected results and it was right. Okay. So avoid the data manipulations. As a precautions, you have to avoid the data manipulations. Okay, virtual experiments may be subject to data to manipulate some errors. So it is important to avoid the manipulating data. Okay, so you have to avoid the manipulating data and use the reliable sources. You have to use the reliable sources. Okay, while you're doing the virtual lab experiments. From us, you have to give the validated. You have to give the reliable sources and have been thoroughly tested and validated. Okay, and protect the personal information. Okay, from protect the personal information. Okay, while you're doing the V labs. Okay, some virtual labs may collect the personal information. So it is important to protect the personal information by using secure credentials and not sharing the sensitive information. Okay, so you have to protect it from the, while you are doing the labs. Okay, now in overall, virtual labs can be useful tool in the education and the research, but it is important to take precautions to ensure safety and accuracy of the results. Two things you have to be very sensitive while you are going on the virtual labs. Okay, one is whether you on the accuracy of your results. Okay, because there is will be some errors. Okay, while you perform your experiments, while you get the results here, there will be some errors. So your main point is whether it was how much it was accurate. Okay, how much it was accurate. Okay, so you have to focus on the accuracy of the results. I give more emphasis on that things. Okay, accuracy is the major part. If your results was not accurate, then your experiment, whatever your experiment you have done, it's not a, it's not an important thing. It will be, it will be, it is not working there. Okay, it is not working. It is not beneficial for you. Doing that experiment. So you have to focus on accuracy. My emphasis on the accuracy, number one priority. Okay, and I will see other thing also, but I have to go focus on the accuracy of the results. So whether it was right or wrong, we have to compare with the other data which are already available, and I have to compare that things, and I'll check the accuracy of the results. Okay. Okay. Now results. Okay. Results from the this experiment I found the from the lab experiment I found the for an AND gate, when both input and input of the AND gate were at 5 volt or high is 1, okay, then output of this gate is nearly equal to 5 volt, and in other case it was 0 volt. Okay, means I found while both input are high and the output will be high, and the other case it will be lower. Okay, 1 1 0. And for OR gate, when both input are the case were 0 volt, the output of this gate is 0 volt. In other cases, we get the output will be high, that is 5 volt. Okay, nearly 5 volt. Because in previously I already shown you that they are in battery. This is the 5 volt battery we are using in that experiment. Okay, so and for the NOT gate, okay, for the NOT gate, when the when input of this gate is 0 volt, then output of this gate is nearly equal to the 5 volt. Okay, for the NOT gate, when the input was low, output was I found the output I found the high in the NOT gate. In the simulations I already shown there. Okay, because while I use the 0 volt input, then the lead was glow or not? It's a glow at the time. I already show you there. Okay, and for a NAND gate, when the both input of this gate was 0 volt, then the output of this gate was at nearly equal to the 5. Okay, and NAND gate is also when both input of this gate was say the low, then output will be of this nearly equal to 5 volt. Okay. Yeah, in the NAND gate, output will be the high if any one of the gate, if any of the terminal of the input was low. Okay, then output high. But in NAND gate, if both the input was high at the time, it will get the low 0 volt. Okay, I've already discussed on that topic. And for a NOR gate also, when both input are at a high voltage, and then output of this gate will be 0 volt. On the other cases, we get the nearly the 5 volt. Okay, if one terminal is low, another terminal is high, then it will give the high voltage, and okay, it will give the low voltage. Okay, not high voltage. Okay, because it is a NOR. For a NOR gate means what? It is for a NOR gate means if one terminal is high, another terminal is means it is high, but is it not or plus not? Okay, so that's why it will be there, give the low voltage. Okay, so for an order, when the both input were at a 5 voltage, then output of this gate was a 0 volt, but in other cases it was equal to the 5 volt. Okay, and when both input were at a 5 volt, then output of this gate was a 0 volt, but in other cases it was uh, it was it was nearly equal to 5 volt. No, in other cases it was nearly equal to when both input are at a 0 volt. Okay, then output of this gate, when both input of this gate are when both input are 5 volt, then output of this gate was the 0 volt. Yeah, yeah. This is when the both input were at the 5 volt, then output of this gate was 0 volt. Okay, but in other cases it was nearly equal to the 5 volt. Okay. Okay, if both not get in the when both input are at a high voltage, and then the output will be the uh, output will be the low. But in the any one case, it will be high and is near equal to 5 volt. Okay, and from this conclusion, I found that from the above lab experiment, for AND gate output was high when both input are high, and when for OR gate output was low when both input are very low, and for NOR gate output was high when both input were low. Okay, and for NAND gate output was low when both input were high. Okay, and we found the high or low output on the variation of input terminal because the input was low, then the transistor is in cutoff state, and the when the input was high, then transistor is in a saturation state. Okay, this is the reasons for the variation of the output. Okay, and this was the conclusion so I found from the experiment. Okay, and these are the acknowledgements. Okay, I like to say thank you for uh, our SOD. Okay, who give this task for me to do, and before him before previously I was not familiar on the VLABs, and what he told me is to about the VLABs. So it was very informative, and I can learn a lot of things from here. And before while I do the experiments, I can perform the experiments and here at my home also. If I have not made, if there was if I have to, if I have not get a chance to do experiments in a real lab, um, if all the equipments are not available in our lab also, I can do the experiments in my real lab and I can learn from there. So I'd like to say thank you for my SOD who give me this who inform me about uh, this website or about this give me an information about the VLab, will tell me about the the concepts of give me an information about the VLab, and I'd like to say thank you for my HOD and the whole faculty of physics, and also as well the whole faculty of physics. Okay, for who give me an opportunity to do their experiments. Okay, and in a real lab also. In a real lab also, I can perform these experiments because it's already available in our lab. And this was my task. In the next week, I'll go to do experiments. Now I've done this experiment in my VLab, and by using VLab, I have done here. So and later on, I'll do in a real lab also. Okay. So I would like that's why I would like to say thank you for all of my physics faculty of CTP, uh, and as a first priority, I would say thank you for our PhD who inform me, who give me information about the lab. Okay, these are the references which I have used here to perform experiments. Okay, all right. Okay, thank you. This is all the slide was finished now, and then I'm sharing you how did I did all these experiments and the lab experiments, the topic of logic gates. Okay, thank you. And I will come again on the different topic on the VLF. And I'm planning to do the VLF before the experience which I have done in the real lab. Okay, I've done this I've done this experiment in VLab, and next week I'll do on the in the real lab. And another topic I'll do on first of all I'll do on the VLab, and later on I'll do on the virtual lab. Okay, and in this way I can enhance my research skills and research knowledge and experimental skills. And so okay, goodbye.